Hello and welcome to The Explainer. Today we're slicing through the science of one of modern medicine's most powerful diagnostic tools, the CT scanner. We're going to see how it takes us from simple shadows to stunning 3D images of the human body.
Okay, let's dive into this. For the longest time, seeing inside the body was, well, a bit like shadow puppetry. A conventional X-ray collapses our three-dimensional anatomy into a single, flat, two-dimensional image. It's incredibly useful, but it's still just a shadow.
And that's the fundamental problem that drove a revolution in medical imaging. How do you unstack that shadow, right? How do you look at a single layer of the body without all the other layers getting in the way? This question is the very reason the CT scanner was invented.
So, the biggest issue with a flat X-ray is called superimposition. Basically, everything is layered on top of everything else. A rib might obscure a tumor in the lung, or, dense organs might hide a subtle fracture. It's just really hard to tell what's in front and what's behind. And the solution is computed tomography. Instead of one flat shadow, a CT scanner takes hundreds of X-ray snapshots from all around the body and uses a powerful computer to mathematically assemble them into a clean cross-sectional slice. It's really the difference between trying to read a closed book versus just opening it to a single page. So how does it actually do that? For that, we need to look inside the big donut-shaped machine, which is called the gantry. This is where all the action happens.
The gantry is just an incredible piece of engineering. On a rotating frame, you have an X-ray source on one side and a highly sensitive detector on the other, always in perfect opposition. This entire assembly spins around the patient at incredible speeds, capturing data from every conceivable angle.
On one side is the X-ray tube. You can think of it as a specialized cannon that generates a powerful fan-shaped beam of X-rays. It's built to withstand immense heat and deliver a precise beam of energy right through the patient's body.
And directly opposite the tube is the detector array. This is the camera. It's a curved, incredibly sensitive sensor that measures exactly how much of the X-ray beam made it through the different tissues of the body.
Now, this technology didn't just appear overnight. The first scanners were painfully slow, taking minutes for a single slice because they had to move in a straight line, stop, rotate a degree, and repeat. The real game-changing breakthrough was the third-generation design you see here, which got rid of that clunky stop-and-start motion and enabled continuous high-speed rotation.
Okay, so the gantry spins and the detectors collect just torrents of data. But that data is really just a long list of numbers. So how does it become a picture? Well, this is where the computed in computed tomography takes center stage. It's like a bit of mathematical magic. The reconstruction process is really a four-step journey. First, the scanner captures hundreds of individual snapshots called projections. If you just stack them all together, a process called back projection, you get a blurry mess, like you see in step 2. The magic is in step 3. A mathematical sharpening filter is applied to the data. Then, when that filtered data is back projected, the blur just cancels out and a clear, sharp image emerges. And this shows you exactly why that filtering step is so vital. Without it, simple back projection creates the star pattern artifact, which completely obscures the anatomy and makes the image totally useless. That filter is what turns this mess into medicine.
For decades, filtered back projection, or FBP, was the gold standard. It's fast and reliable. But today, many scanners use a new, more powerful technique called iterative reconstruction, or IR. Instead of a one-shot calculation, IR starts with an initial guess and then refines it over and over, getting closer to the perfect image with each loop. So why use this more complex method? This chart explains it perfectly. Iterative reconstruction produces clearer images with significantly less noise. And the most important benefit? It can do this while using a much lower radiation dose to the patient. That's a huge win. All right, let's move to the final image itself and see how doctors and radiologists actually read and interpret these amazing pictures. When you look at a CT image on a screen, you see a grid of tiny squares called pixels. But it's important to remember that each 2D pixel actually represents a 3D cube of tissue inside the patient. This tiny cube is called a voxel, or a volume element, and it's the true building block of a CT scan. The computer assigns a brightness value to each voxel based on its density.
using a standardized system called the Hounsfield scale. This creates a universal language for CT. On this scale, air is defined as -1,000, which appears black. Pure water is the 0 point, and dense materials like bone have high positive values, making them appear bright white.
And this highlights the fundamental trade-off in every CT scan. See, a higher radiation dose creates a smoother image with less graininess or noise. But because radiation carries risks, the guiding principle is always ALARA, using a dose that is as low as reasonably achievable to get a clear diagnosis.
Now, this technology didn't just give us a new way to see inside the body. It completely changed the practice of medicine across countless specialties.
One of the biggest drivers of this change has been speed. The rotation time of a modern gantry is more than 500 times faster than the first clinical scanner. What used to take minutes now takes less than a second, which has opened the door to applications the original inventors could have only dreamed of.
This incredible speed allows doctors to freeze the motion of a beating heart, instantly assess injuries in a trauma patient, find and track tumors with millimeter precision, plan complex surgeries, and even perform virtual fly-throughs of organs like the colon, a technique known as virtual colonoscopy.
We've come a long way from the early CAT scans, which only produced axial slices. As this quote notes, modern scanners can create voxels that are perfect cubes, what we call isotropic resolution. This means we can reformat the data to create flawlessly clear images from any angle, coronal, sagittal, or any oblique plane you can imagine.
So the journey has been truly remarkable. We've gone from interpreting flat, overlapping shadows to building and exploring interactive, three-dimensional models of a living person's anatomy. It is, without a doubt, one of the great technical stories of modern medicine.
To go from flat shadows to interactive 3D models in just 50 years is astounding. It leaves us with a fascinating question. If this is where we are now, what will medical imaging reveal in the next 50 years? Thank you for joining this explainer.